Hi there. Now we are going to discuss about some operations that can be performed on images like AND, OR, and NOT. As in digital electronics we have logic gates. We can perform similar operations on pixels on an image. Generally 255 is represented as white and 0 is represented as black in digital images. If we perform AND operation between two pixels, the output pixel will be white if and only if both pixels are white, and it will be black in all other cases. Now, suppose if we perform OR operation between two pixels, the output pixel will be white if one of the pixel is white, and it will be black only when both pixels are black. Now, coming to the NOT operation, it is a unary operation. It basically inverts the pixel from white to black and black to white. Now let's see operators in action. Here I have imported the CV2 module and CV2 underscore IMShow function from the Google Colab. Also I have read two images that we will be using. The first image is a background image and other one is a circle image. Now let's try applying the operations that we have learned like AND, OR and NOT to the image. For that, let's create a new variable to store the AND operation image, and we use bitwise AND operation in the CV2 module. Here the first parameter is the image and also the second parameter is also the image. Now there is one more parameter called mask, which we provide as a none. Now let's see what is the output of this operation is. Now you can see the AND operation between these two images looks like this. Now here the order of the images that we have provided does not have any priority. Even we can provide the circle here and the background images here. Now the mask is mainly used to apply the AND operation for a specific region if we are interested in an image. So we can basically define the boundaries of particular region in an image and perform the AND operation by providing one of the images here. So it will be only taking that particular area in one image. Now let's see how OR operation is being performed. For that, I will create another variable to store the image array, and similarly we have a bitwise OR operation, and I am passing the background image and the circle image, and similarly the mask is none since we have to perform the OR operation on the entire image. Now let's see how the image looks like. Now you can see how the OR operation being performed. Here the white pixel has been joined together and the black remain as it is. Now let's perform NOT operation on an image. Now as I said earlier, NOT operation is a unary operation. It means that it only requires a single image to perform. Now let's use the CV2 bitwise NOT operation for this. Now if you want to invert the circle image, and here also we can define a mask as none. Now let's see how it looks like. Here you can see the image, circle image has inverted. The white becomes black and black becomes white. Now let's see what is a kernel. A kernel is also called a convolutional matrix. It is a small matrix, as you can see in the image. The subscript that is being denoted in red color is the kernel. A kernel is having fixed value for a particular operation. Here you can see the kernel elements get multiplied to the pixels on the image, and the sum of the values of each matrix is being shown on the right side as convolve feature. Differently sized kernel contain different patterns of numbers, produce different result under convolution. Now, the size of the kernel is arbitrary, but 3 by 3 is more generally used as shown in the diagram. Now, the process of sliding the kernel over an image is called a convolution. A convolution is a mathematical operation between two functions f and g that produces a third function. A convolution is done by multiplying a pixel and its neighboring pixel color value by a matrix. Now, you may notice that the pixels on the corner and edges are much used less than that of the middle. So, suppose in the right side you can see the pixel A is only touched once in a convolution operation, and the pixel B is touched 3 times, while the pixel C is touched by 9 times. In general, pixels in the middle are used more often than that of the borders. So A is only visited once and B is visited thrice and C 9 times. To overcome this problem, we use the concept of padding. As you can see, there is a gray border that is being added. Now, in order to avoid this problem, the concept of padding, in which we add a layer of zeros to our output images so as to avoid the problem as we see. Now let's see what a kernel is. Here I have read an bottle image and resized into 500 by 500 pixels just to make sure it will fit into this window. Now let's try applying one kernel to the image, which is mainly used for averaging. Now, in order to perform the kernel on an image, we need to import an module called NumPy, which is used for mathematical computing. For this, we need to type import NumPy, and in order to represent in short form, we name it as NP. Now, we define a kernel, which is a NumPy array np.array, and here we are defining a two-dimensional matrix in which every element, that is 3 by 3 matrix, as 1. Now, in order to make this kernel as an average blur, we need to divide it by the sum of the total number of elements in the array. For this, I am multiplying it by 1 by 9. Now, this is a 3 by 3 kernel. Now, in order to apply this kernel into our bottle image, we need to create a new variable that will store our new image after applying the kernel operation, and we use a function called filter2d in order to achieve this kernel operation on an image. Now, the first argument is a source image, and the second argument is a depth to the output image. Now this is something that we have very less importance. Here you can see the source image is passed first, and second is the depth of the output image, and this depth of the image is belongs to the destination output image where we have to store the image. So this is, as a third argument we pass the kernel that we have created just now. Now let's see how this operation on the image performs. Now here you can see the image got bit blurred than the original one due to the kernel operation. So here the first parameter is a source image, and the second one is mostly given as -1, and the third is kernel that we have passed. And we can play with this kernel and these values, which will give different output for the image. Now let's see what is called smoothing or blurring. This operation is commonly used in image processing to reduce the image noise. In this process, it helps in removing the edges from the image and make it smooth. In general, blurring is achieved by convolving the image through a kernel. Now let's see what an average blur means. During this operation, the image is convolved with a kernel with a particular height and width. Now, it is also to be noted that it is divided by the total number of cells in the kernel. Now, in this process, the central element of the image is replaced by the average value of all the pixels in the kernel area. Now let's see what a median blur does. In median blur, the central element of the image is replaced by the median of all the pixels in the kernel area. It does not create a new value. So the filter preserves the edges and rounded corners. It is used to reduce noise, especially salt and pepper noise, and delete scratches from the photograph. Now let's see what a Gaussian blur does. Here you can see from the equation, it is an exponentially decreasing function with one argument as x square plus y square, which is an equation of circle. So you can see that the priority of the pixel that is being considered decreases as its distance from the center pixel increases. Now, Gaussian blur is a result of blurring an image by a Gaussian function. It is widely used to reduce the image noise and reduce detail. Gaussian blur doesn't weight each pixel equally. However, the closer a pixel is to the center, the greater it affects the weighted average used to calculate the new center pixel value. Now let's see some smoothing operations. OpenCV has some inbuilt smoothing operations that can be directly accessed by its functions. Now, as usual, I have imported the bottle image, and this is a bottle image. Now let's try blurring the OpenCV image using the blur function in OpenCV, which is cv2.blur, as simple as that. Now we pass the bottle image, and the next one is a kernel size that we require. We can present it as a tuple, and now let's see how the image looks like. You can see how easily the image got blurred without even thinking or making a new kernel. Now let's see other types of blurring operations like Gaussian blur and median blur. Now here I have loaded an image that is containing some noises, and this noise is also called salt and pepper noise. So in this image you can see there are too many greens in the image, which can be removed using the Gaussian function. Now let's see how we can do this. First I will define a new matrix which can store the image, which is can be named as Gauss, and now we access the Gaussian blur function from the OpenCV and pass the bottle noise image. Now here you can see the first parameter is a source image and second parameter is a k size. This represents the kernel size which is to be provided in tuples. Now other parameters are sigma x, sigma y, and DST is the destination output image. Here you can manually define the standard deviation along the x direction and standard deviation along the y direction of the Gaussian function as we have discussed in the presentation. Now there is also one more parameter called border type, in which you can provide any values that you require to be provided as a border of the image. Now let's not worry about sigma x and sigma y and provide the kernel size as 7 by 7. And the next parameter that I am going to use is a border type, which is 0, since we don't need any borders. Now let's try displaying the image, that is bottle underscore goals. Now the noise has been significantly reduced in this mesh. There were too many points here. Now the points has been reduced a lot. Now let's see how a median blur works. For this I am using the same image of the bottle noise. Instead of the Gaussian blur function, we are going to use median blur. Bottle underscore median. So now we are going to access the median blur function, and here I am passing the bottle noise image. And here you only require to perform the kernel size as a single number, since that will be automatically making entirely an two-dimensional matrix. So here we can just directly pass as 7, and let's see the output. So here you can see the median blur takes the average value of the each kernel area. So here the noise is reduced much more when compared to the Gaussian. So each of the smoothing operations has its own benefits and functionalities that will be useful for image processing.